Now let's look at second law analysis of vapor compression refrigeration cycle. Consider the vapor compression refrigeration cycle operating between a low temperature medium at T sub L and a high temperature medium at T sub H. The maximum coefficient of performance of a refrigeration cycle operating between temperature limits of T sub L and T sub H is given from the equation COP maximum would be equal to COP refrigeration of a reversible system would also be equal to the coefficient of performance of a reversible Carnot system, and that would be equal to T sub L divided by T sub H minus T sub L, or would also be rearranged to be equal to 1 divided by TH over TL minus 1. Actual refrigeration cycles are not as efficient as ideal ones like the Carnot cycle because of the irreversibilities involved, but the conclusion we draw from above equation is that the coefficient of performance is inversely proportional to the temperature ratio TH over TL is equally valid for actual refrigeration cycles. And the section below this on second law analysis that has associated with exergy could be skipped for this class. Now let's look at selecting the right refrigerant or factors that should be considered. When designing a refrigeration system, there are several refrigerants from which to choose, such as chlorofluorocarbons like OCFCs, hydrofluorocarbons, HFCs, hydrochlorofluorocarbons or HCFCs, ammonia, hydrocarbons like propane, ethane, ethylene, etc., carbon dioxide or air in the air conditioning of aircraft, and even water in the applications above freezing point. The right choice of refrigerant depends on the situation at hand, and I would invite you to look at the this section in the textbook to get a better understanding on the factors that you should be aware of when selecting the right refrigerant. Now let's look at heat pump systems. Heat pumps are generally more expensive to purchase and install than other heating systems, but they save money in the long run in some areas because they lower the heating bills. Despite their relatively high initial costs, the popularity of heat pumps is increasing. About 1/3 of all single-family homes built in the United States in recent years are heated by heat pumps. The most common energy source for heat pumps is atmospheric air or air-to-air systems, although water and soil also can be used in heat pumps. The major problem with air source systems is frosting, which occurs in humid climates when temperatures fall below 2 to 5 degrees C. The frost accumulation on the evaporator coils is highly undesirable since it seriously disrupts heat transfer. The coils can be defrosted, however, by reversing the heat pump cycle, running it as an air conditioner. This results in a reduction in the efficiency of the system. Water source systems usually use well water from depths up to 80 meters in the temperature of 5 to 18 degrees C, and they do not have a frosting problem. They typically have higher coefficient of performances but are more complex and require easy to access a large body of water such as underground water. Groundwater systems also are rather involved since they require long tubing to be placed deep in the ground where the soil temperature is relatively constant. The coefficient of performance of heat pumps usually ranges between 1.5 and 4 depending on the particular system used and the temperature of the source. A new class of recently developed heat pumps that use variable speed electric motor drives are at least twice as energy efficient as their predecessors. Heat pumps and air conditioners have the same mechanical components. Therefore, it is not recommended to have two separate systems to meet the heating and cooling requirements of a building. One system can be used as a heat pump in winter and an air conditioner in summer. This is accomplished by adding a reversing valve to the cycle, as you can see in this figure. As a result of this modification, the condenser of the heat pump located indoors functions as the evaporator in the air conditioner in summer. Also, the evaporator of the heat pump located outdoors serves as the condenser in the air conditioner. This feature increases the competitiveness of the heat pump. Such dual purpose units are commonly used in motels. Heat pumps are most competitive in areas that have a large cooling load during the cooling season and a relatively small heating load during the heating season, such as in the southern parts of the United States. In these areas, the heat pump can meet the entire cooling and heating needs of residential or commercial buildings. The heat pump is least competitive in areas where the heating load is very large and the cooling load is small, such as the northern parts of the US.